In this video we're going to talk about the single slope ADC, which is an analog to digital converter that is very important since it's a stepping stone to something more important, which is the double slope ADC, which we will see in another video. But to understand that, we first need to understand the single slope ADC. So how it's made is, this is just a part of it, it's not the whole ADC actually. Is the first part, which is an integrator. And how an integrator works is that it integrates a signal. In this case it will be a constant signal, and if you integrate something constant you will have a slope. So that's why it's called a single slope ADC. Okay, so we have something like this. Okay, and this right here, this output, which is the slope, I will just paste it below, will be fed into something that is called a comparator, which looks like this. Okay, so here we have the first output and we have V in. V in is what we actually want to convert. Since we're doing the analog to digital conversion, we have to convert some analog signal, some analog voltage. So this V in is what we're gonna actually convert. How this comparator works is that we'll write this output as the second one, so VO2. So VO2 will be, as long as V in is bigger than V out 1, then the second output will be positive. If the moment it becomes equal and a little bit smaller, okay, so we'll write V in equals to VO1, this exact moment the output will turn 0. Okay, so first to understand some things, let's calculate about the integrator, the formula. So the formula for an integrator, it looks like this: V out equals to -1 divided by RC V in dt. So here above we had VO1 as our V out, which equals to -1 RC multiplied by our input, which is minus Vref. Okay, so let's just write that very good in our formula. So that's VO1 equals to -1 divided by RC times minus Vref. Be careful here, the minus sign is important. So since we have two minuses, we can just write it as a plus. Vref dt, which is equal to, if you integrate it, Vref here is independent of t, so we can take it out of the integral, and then we have Vref divided by RC, which was this was taken out of the integral, and then we have just dt, which is simply t if you integrated it. Okay, and so we got as a final thing that VO1 equals to Vref divided by RC times t. That's what we got. But we also want to see, we are curious, when will this right here happen? When will the V in become VO1? So to understand that, we can write that V in is also equal to Vref divided by RC times t. Okay, so as you can see here, t is directly proportional to V in, which means the bigger V in is, the bigger the signal that we want to convert, the more time it will take for the ramp to go up. Okay, so let's say if it's 2 volts V in, so maybe it will take this much time, right? But if it's 4 volts, maybe it will take this much time, which is what we exactly expected. Okay, so afterwards, after this happened, let's see what happens next. So I'll just rewrite it here for clarity. So this output goes into an AND gate. Okay, it has a clock here, and then there is a counter, and then we have the binary output. So don't worry, it sounds and it seems a little bit scary at first, but I will exactly explain what's happening here. Until now we saw the functioning until here, so let's just continue. Afterwards, until V in is bigger than VO1, here we will have an output of 1, as we said before. And the AND gate, if you don't remember, I'll just remind you, this is an AND gate, and the only way it can have an output of 1 is if both of its inputs are 1. So that means that until V in is bigger than VO1, VO2 will be 1. That means that here the AND gate will have an output of 1. It means that also the counter will count. The moment that V in becomes VO1, VO2 becomes 0, which is this thing right here. So as we said, if one of the inputs in the AND gate is 0, at least one, let's say this, also the output becomes 0 right here. So this also becomes 0, which means that the counter doesn't receive a signal, so the counter stops counting, and then we have our binary output, which means that the counter is proportional to how much time the ramp goes up, so it's proportional to t. But before, right here, we said that t is proportional to V in, which means that the counter is proportional to V in. Okay, so you saw this logical reasoning, which means that the bigger our voltage we want to convert, the more time it will count, and as a consequence we will have a bigger number in our output. The smaller the voltage in our input is, the less time it will count, and the smaller the number we get into the output. And this is how this single slope ADC exactly works. So we've successfully managed to convert a voltage into a binary output, and the only problem with this is that, as you can see here in the formula, we have RC here that will sometimes not be stable because of temperature and aging and stuff like that. But we have a very good way to resolve this with the dual slope ADC, but that's a topic for another video. I hope you enjoyed this one, and see you in the next one.